So I work at Barefoot. I'm responsible for product management of the deep inside analytics. I also work as product manager for a number of these advanced applications. So add touch base over load balancer, things that you can do thanks to the programmability of the chip. Prior to joining Barefoot, I was part of the NSX team at VMware, and so I've been there 4 years, pretty much since the beginning. So I'm pretty happy to be back at VMware. So starting on telemetry, before we jump on the deep inside, let me give you a quick overview of the technology. And that's specifically what we are doing there to make it useful for customers. So at Barefoot, we start asking the question, what should we do to really make this telemetry something useful, very accurate for customers? And we came up with, answering to these 4 questions. The first one is basically be able to say which path this packet took in the network. This is not straightforward, specifically if you have equal cost multipath, if you have flowless switching and certain optimization in the network. And so this goes back into kind of tracking the journey of that packet through the network and find out the transit latency, which is what typically for the switches give more the variable latency for these applications. The second question is fundamentally going back and try to explain or find out which rules were enforced. So why this packet got here, which rules were enforced to forward the packet. And so this goes back into finding out the subnet lookups, which ACL were enforced. This is a way to prove that the data plane is actually implementing the policy from a security standpoint that I was supposed to push in the network, was also, from a capacity planning standpoint, has been very well designed. And a couple of other questions that pertain more to the performance of the network are related to things like, can you tell me which one are the hotspots and the congestion points in my network? This goes back to kind of trying to track the performance of the network related to these applications. And the last but not least, when you encounter such a congestion, be able also to say, can you tell me a little bit more about that congestion? Not just tell me there is a problem, but give me kind of the root cause analysis. So in this particular scenario where I have like an application that is misbehaving and is acting as an aggressor flow and is consuming the bandwidth, can you tell me that? Can you tell me more? So instead of doing long troubleshooting workflows, with few clicks, I can find out about this problem, right? So we call this the 4 ground truth questions of network telemetry. And we believe with Tofino and Deep Inside, we can answer them all with no impact on performance. All this telemetry in pipeline alongside with other features in these data planes. Tofino is one example. There are other examples that will bring up smart NICs that are implementing this. And so it can be done at full line rate without generating any additional packet. Instead of generating probes, which typically are inefficient, you turn every application you care about into an active probe. So let's talk about how we do this. So this sits on top of a technology called inbound network telemetry. So going back to what Ed just described, the p4.org independent organization, this is an open specification that you can find if you go on the GitHub on p4.org. You can download. So it's definitely open. We really thrive on open source and open communities to bring in new ideas and to build this open architecture. And how does it work? The concept is pretty simple. So you have this INT domain. You always have an ingress point in this inbound network telemetry network. So that ingress point is called the INT source. The INT source node in this case is a switch, is a network switch. But can be very well like a smart NIC, or can be very well an hypervisor, or kind of an edge element that is before the switch. So that INT source instruments packets for telemetry and tell all the following switches along the path which type of telemetry data should be collected. So other devices, for example, like the INT transit devices, can read the instruction set that is written in this INT header and add more metadata. Eventually, that metadata has to be removed before you deliver that packet to the application. You don't want to change your application stack, so all this instrumentation has to be transparent. And that INT sync node will remove that metadata and deliver it to an analytic appliance, in this case, Deep Inside. Right. All of this can be done. Of course, the more end-to-end devices and the more programmable data planes capable devices you have along the path, the better, because you get more visibility. But all of this can also be done in a brownfield. The system, the architecture, has been designed to work in a brownfield. You can have a single device. Question?
You don't require two phenochips everywhere along the path in order to get the visibility.
Correct. You can have even a single device and stream the telemetry, looking at every packet going through that device. You can have what is more typical is customer will start upgrading the top of the racks where they have the cluster that are more sensitive to these performance issues. So, and while the spine layers, for example, are not capable. So in this typical sandwich scenario, the telemetry works perfectly. If you have one hop that is not INT capable, you can still infer a few information there, like the path and some of the latency information.
Is your software going in and making these changes automatically, or from an IT perspective, does somebody have to look at the analytics and then say, yes, we want to redirect the way?
That's a great question.
Going?
So there is you always start, telemetry is always is a journey. So you start, for example, learning about your application. You start discovering what's going on. So you typically turn on these features, and I'll describe a little bit in a second what are these capabilities. And then based on what you observe, the number of flows, the problem that you discover, you can turn on a little bit more of that telemetry. So it's kind of an incremental process till you baseline the traffic and the application in your network.
But the consumer has the ability to make the choice.
Yes. The consumer, in this case the user, has the ability to make these changes. I'll show you in our demo, we have a Cisco Nexus box, so you can configure this feature the way you configure today any other feature in Nexus.
This looks very similar to in-band OEM in terms of like capability. I mean, V6 in-band OEM is sort of unique in terms of where it's positioned, but it looks very similar. How are you handling like, NFV insertion and like other components that are around that? Because that becomes a little bit more complex in terms of what happens here. You can obviously, in the sandwich mode, you can catch it on either end because you see the headers, but in between on the transit side, I see that still as a problem, right? You don't know if someone intercepted, did an NFV insertion, came back out, and passed.
Yeah, that's a great question. And on the inbound OEM, we are actually actively participating in the definition of these specs. We actually participated to a hackathon at ITF 100, where we demonstrated like how inbound OEM can be implemented onto Pheno.
Okay.
And these are more complex scenarios, of course. What I'm highlighting here is typically a data center scenario. That's where you get more complex encapsulation. You need to leverage things like NSH to insert these telemetry data. You need to also, sometime when you have things like function network virtualization, you need to make some of these VNF aware about the inbound OEM. So that goes into that kind of.
Yeah, it looks really complementary in terms of the capabilities of because you can get two sets of telemetry data at the same time and be able to guarantee one in one flow path, and then be able to match that up to the identified flow path that you guys are doing here.
Exactly.
Okay.
So is this going to be able to do application dependency mapping?
Yeah. So today, how we discover the application. At the network level, we track this application based on 5-tuple information. We have source IP, IP addresses, port numbers. So at that level, we can detect a certain application. We don't do specific like deep packet inspection to find more about that application, but these are certainly possibility where you integrate, for example, with a DPI agent that does that application detection and insert that app ID as metadata inside the packet. So in that case, in future will be possible to do such things. So this was certainly one of the first use cases that we brought, and we've seen becoming very popular with customers. And there was a lot of learning from this INT. So throughout all the different proof of concept, production trial, and implementation, we learn about how to make INT production worthy and production ready. And so we built a number of capabilities on top of INT. We call this smart programmable real-time INT. Smart because, yes, you can instrument and observe every packet, but when you do that, you add some metadata, so you're going to consume a little bit of bandwidth. So some customer may like to select specifically which application they want to instrument. And again, this can be based on the SLA, the performance characteristic. Also, as there was previously a question, can the user control what needs to be collected? These are certainly possibilities. You can go in these switches. You have a CLI API command to turn on and off the collection of specific metadata. Intelligent triggers, this is more of a functionality that goes on that INT sync node. In these networks, you have millions, billions of packets per second. You don't want to generate billions of reports per second. No analytic engine will scale to digest all this information. So the key point here is to use these triggers to define what an anomaly means for you. And the very basic trigger could be a threshold. So tell me when the latency grows beyond a certain point, tell me about that. Let me know about that. When there is a packet drop for a specific reason, I'd like to know about that.
So when it comes to collecting, and do I also have the ability for redirecting, so collecting, I want to collect video traffic as it comes in, but I want to know people are going to Netflix, but I don't want you, Game of Thrones, showing up and collecting a full copy of that and ingesting that. I just know that's where you went for that moment, and I'm discarding the rest of the traffic. And would I have that same flexibility in a way of redirecting that traffic to some external entity for collection or any other further analytics?
Yes, this is totally complementary and compatible with all the existing techniques. So you have a year span, redirection of traffic. You can even send this telemetry traffic to a number of applications or appliances.
I like to think of sending this traffic off to Splunk for further later analytics and keeping online, but I don't want to, because I'm paying per gig, I don't want Game of Thrones sitting up there. They're binge watching, and all of a sudden my cost just went through the roof.
Yes. So there are.
Yeah, and so I think that's one of the things about the smart is that you don't send an entire packet, right? Just send the metadata. That's another way to save on your gigs of Splunk cost as well.
Because that's a real big problem I see in a lot of environments. And solutions have come to bear specifically to address that as a way to allow you to actually collect the data and get the reporting you want, but not have to store that burden.
Yeah, and so that's one of the key things about this is it allows you to just send the metadata and not the entire payload.
Do you have flexibility and control of sending that data because you're only sending the metadata, or can you actually send the full packet data, and then can you act upon that data if I've got PII and GDPR?
Yeah, you have that flexibility. So in order to save in terms of bandwidth, we today truncate the packet, but that's programmable, and the user can decide to.
Because I want the transaction, I want that a credit card was passed, but I also don't want to store that credit card because now I'm entering into different types of PCI problems, and I don't want to expand the size of the the zone of audit.
Right. So another characteristic of this intelligent data plane is, let's say, hey, I'd like to do this monitoring on these 3 different applications, and there is a lot of traffic involved, a lot of anomalies. So you have a built-in load balancing capability, so you can redirect telemetry for specific applications or flow to different collectors. So you can scale out your analytic backend here. The programmability is a critical aspect. The telemetry is not the same thing for every customer, and every customer has its own idea where to put the metadata, what type of metadata to collect. So having P4, that gives great flexibility there. Also, P4 being a platform-independent programming language allows to port this program on different targets. Today, we have open source and INT program that can be deployed on, of course, an our Tofino chip, on a number of smart NIC and bare metal and OVS data planes. Last but not least, real-time is an important characteristic. We do all of this in the data plane with a push model. We don't require any agent to be involved on the control plane or the management plane. So this makes truly that real-time and not subjected to any bottleneck from a CPU standpoint. And that allows finally these analytics to get the real-time notifications and visualize in the dashboards. And I'll show that during the demo.